Hello, everyone. Thank you for coming here, and thank you for the organizing committee for putting up this event. I'm here to present a work that I've been working on with my supervisors and also collaborators at Delphia as part of my PhD, which is also funded by Delphia, which is a fintech company based here in Toronto. So the project, to give a little bit of a summary, basically comes from an initial motivation that is concerned with forecasting fundamental data. So this is something that has been, so this is what started this work. Well, I'll just go right into it, basically. So the initial motivation comes from an observation that has showed that for predicting future values of fundamental data, so anything that you might find in earning reports, which are published quarterly by public companies, such as the earnings, the sales, and so on. Well, having this information, having the future values of those values at the present time has been shown to be quite an effective portfolio construction strategy. So here, having this information months ahead of time actually shows that we can get quite high returns. And now this is for having perfect knowledge of those values, but usually you don't have access to perfect knowledge, and you have to be happy with a somewhat lesser accuracy. So there's models that have been built to predict those kind of values. They usually use conventional data, but a new trend has been to incorporate alternative data. So anything from transactions on a credit card, geolocalization data, social media sentiment can be considered an alternative data sources. And what they brings that conventional financial data do not have is, well, like at least some of them, they're more timely. So you have, instead of a quarter observation, a value observed every quarter, we have more frequent observations. They also bring information that you will not find in more conventional data, so stock prices, earning reports. So any information that can give you an edge is important in that type of problem. But they come with some challenges, which is, first of all, they can be quite hard to access. So to get those sorts of data, you actually need to put a lot of work to build the pipelines. It can be costly, it can be hard to also merge with the traditional data. If you have text data, it needs a lot of processing and so on. So a question that we were led to was, because of those constraints, can we just start with a low sample of alternative data, and from this low sample, integrate that into the model, use it for the prediction that we are interested in, but on top of that, also extract that value, extract some information for that low sample to complete the remaining unknown values for these alternative data sources. Another question, which is related, but I will not cover in this presentation, but is very much part of the project, is how can we also use this small sample to guide the acquisition of additional observation. So instead of just estimating the possible value, actually acquiring, so at a cost, what kind of other sources should we put our effort into? So that's, so one way to incorporate the data is simply to integrate it into a single data set. That's an example that you can have, pretty typical. So for Okay, so for the entities here, we have some observation over time. This would be our alternative data source. So a lot of those are missing here because we only have some observation for like an entity, missing for all the others. That's a kind of missing patterns that you might observe. So something that is like block missing for Apple, something that is missing over time here or a sequence or across a whole entity in this example. I'm having a bit of trouble with the red lights, but I think you see what I want to show. And in this example, we will be interested in predicting the earning surprise. So to solve this, first to kind of like give a better view of the missing patterns that we are considering. So we would have we observe maybe some random pattern, so randomly distributed, no clear pattern. A second type would be, as I showed, like a sequence of time over which we have no observation. The same can be done across the companies. And then we can have like a mix of both and have a complete block missing. It's kind of like the four type that we might observe. And to address this issue, a very natural set of techniques are imputation techniques. The standard imputation techniques would be simply replacing the missing values by the mean, the mode, the last observed value, the most frequent value. Then we have more advanced technique. I will not go into them, but if you recognize any, which are pretty well known, which is like the maximum likelihood, trying also cluster based, so using the most similar data point to and average the values to get the missing one, interpolation, such as those. Those have limitations. So usually they will work well in 1, 2, if you're lucky, maybe 3 type of missingness pattern. So for instance, if you have a block missing, you might not be able to get a great performance with a local method that use the surrounding data points of that missing value. So, and another difficulty is that limitation is that they do not necessarily use all the structures that is present in the data, and that is actually really helpful to recover the missing values. To give some examples, if you look at the S&P 500 companies, you have you have a temporal pattern that is observed during a year, which is, okay, I'm sorry, I'm having troubles. Okay, so where we have a clear seasonal patterns during the year. I don't know what's going on here. And on the entity side, we also have some cluster of company based on the industry from which they are part of. So if we can leverage all the structures that is within our data set, then we can probably have much better recovery accuracy of the missing values. So a more informed technique has been proposed, which is named multi-view imputation, and is really addressing those two limitations. What it does is that it's going to have 2 views, so a global and a local view. The global view is especially useful when you have those block and monotone sequential missing pattern, because it will be using the whole data set to kind of have the estimation of the missing value, which would fail for the local variation. The local variation can also be very helpful in some cases. So the mix of the two is very useful. Sorry about that. And for each of those, we have a focus on different structures. So that can be temporal and spatial. So that's sort of come back to what I showed here. But you can really imagine other type of structures. This is just a simple example. So spatial can be a hierarchical, it can be network, it can be clusters, it can be like many types depending on the data that you have. So each of those parts of the model, so those will be, so the global temporal, global spatial, and so on. Each of those will focus on a specific aspect of the data. And at the end, you will have an ensemble. You will take all those estimations, put them together to get some kind of estimation for the missing values. And in this paper, they propose to choose the weighted average, where the weights are selected by the combination that minimize the mean squared error. So as I said, it is quite robust to across different missing patterns because of the local and the global view. But it is also adaptable to different data structures because of the different models that can be selected as part of the ensemble. Yeah, and so that's the presentation for the multi-view imputation. And what we've been interested in is to have a look at like a more deeper look at what this method is able to really do. Mostly it's been used on specific application, but we wanted to kind of see if we give it different kind of structures, how well does it compare to other baseline methods, and how well it is able to capture the different structures inside. So, sorry. On the left, you will have like a very simple clustered sine waves. So very simple temporal and cluster pattern. On the right, we have like a more complex temporal pattern, but also with this kind of same clustering of series. These are all synthetic data set, by the way, and they're obtained by just generating one and slightly shifting the phase or the amplitudes. Then we have slightly different data also. So this is another autoregressive. Again, the same cluster pattern is present in this, generated in the same way as the two previous one. And lastly, this is a real data set. This is each series is basically the values of each series is the amount of cash withdrawn at different ATMs across the UK. And so with this gives us some various data sets presenting different kind of structures. And now we are going to introduce some of the missing patterns that we've seen previously and evaluate how the multi-view imputation does. And we evaluated by using the MACE metrics. So this is simply taking the error and scaling it by the performance of a baseline method. Here it is the one-step naive forecast, so just predicting the next value as the previous one. And that is done simply to get a better comparison across different data sets. So this is the results we have on the first type of missing pattern. What we see is that the multi-view is always in the top three methods as measured by the MACE. But what is actually quite remarkable is, and that sort of makes the point, is that when you look at the two top, we have both the interpolation and the fill forward that are on the top, in the top tree. But as soon as you change the data set, they become the last two best performing. So you have a very, very sensitive performances depending on what kind of patterns you have. So the other thing that we see is that when you have a monotone missing pattern, the multi-view imputation is always the top performer. And that is again because of it is able to really make the best out of any situation that you presented, thanks to the global and the local methods inside it. So now this is still in the early work. We still want to do more experiments. We want to extend the benchmarking that we've started. We want also to, so across various structures, see how well we can recover them, like especially, especially having like some idea of like, we have this kind of structure, how much is this model able to model it? And in the second part, we want to apply this method to the problem we introduced initially, which is the problem of fundamental forecasting with alternative features, and when we only have a low amount of observation. Initially, we will have a first look at what kind of structures is present in the data set, because this will inform what kind of model we want to have for each views of the multi-imputation. And then compare the performances, the forecasting performances, when we have this imputation technique versus others. So to summarize, I hope I'm good with time. Okay. So to summarize in 4 points, we have this problem of fundamental forecasting that is motivated by the fact that we want to, that is motivated by the fact that we know that if we have those future value at hand, we can have a very lucrative portfolio construction strategy. Having those, having observed that, incorporating alternative data can be a very, very like a good way to increase the accuracy of those predictions, but it comes with the difficulty that is costly and hard to access. So to address this, we have this idea of only using a small sample, and from this small sample, recovering and reconstruct the remaining unavailable missing points. And to do that, we've turned to multi-view imputation, which is able to take into account the structures in the data and which works well on different sparsity scenario, as we have in the data that we are concerned with. And the future work will be focused on extending this kind of on assessing the performances of multi-view on the fundamental forecasting problem using alternative data. So that's it. Thank you for attention. Happy to answer your questions.